Welcome back. In the last video, we covered data pre-processing, and I gave you some examples and some motivational example to explain to you and highlight the fact of the need of pre-processing. And we cover the one of the method, which is the standardization or removing of mean, which is this one here. So basically taking all the data minus the mean of and divided by standard deviation. It is also called variance scaling as well, because we convert everything to basically Gaussian with zero mean and unit variance. Alright, so in this video we're going to cover min-max or scaling the features to a range. Now, scaling features to lie between a minimum and maximum value. Now, quite often it's between 0 and 1. This is so that the maximum absolute value of each feature is scaled to a unit size. Unit size here, again, just to emphasize, is between 0 and 1, 1 being the maximum. Now, the motivation of using this scaling, basically including robustness to a very small standard deviations of features and preserve the zero entries in the sparse data. This will really speed up your algorithm substantially, and it's quite a popular one at that. Now, scaling this as I mentioned before, this is to scale the data to between 0 and 1. The so-called library here, or the method here, is called min-max. Again, we have some training data. We are importing or instantiating the min-max from the pre-processing library from scikit-learn. And we transform our training data to xtrain min-max. And as you can see here, the data has all been transformed to between 0 and 1. The lowest number being -1 is now 0. The largest number of 2 is now 1. So basically the largest number becomes the max number becomes 1, the lowest number becomes the min. So hence everything is between the 0 and 1 range. Now, applying to unseen data, we call it xtest, and we have simulated as -3 and 4 here. Let's just see what it looks like. And with that, because the 4 and -3 is not within the original train, this is probably a really bad example, but as you can see here, it actually does allow it to actually go above that. Ideally, your training data includes all the possibilities and more or less contain or capture the feature. But in this case, if it's within, like -1 is within, it gets transformed to 0. Whereas the other two number, -3 and 4, is outside the range. It gets transformed to basically, again, from a distance wise, it actually captures that. So let's add a few more examples. 2 and 4, 0, 2, and let's just try 1.5, and let's see what this looks like. Oops. Alright, so it cannot broadcast with the shape of 163. Okay. Alright, what happened is that the shape itself must conform to the 3. Okay, 3 in an array. So I've transformed this, and what you can see here now is that the -3 is still outside the range of our training data. Is captured here. Again, the 4, which is outside of our training data range, is captured here. The rest is transformed as per expected. Alright, so let's get into the rationale of min-max a little bit. What is the transformation that's being done here? So basically what you have is it takes the data minus the lowest number and divided by the range, okay, from the max minus min. And basically that's actually how it transformed the whole data itself. First, it actually standardizes it, okay, and it takes the max minus min and then add the actual min itself. So basically it takes the x standard, multiply by the range itself, and then add the min to it. So ultimately it's actually a distance-based formula. Now you can actually look up the documentation, and we'll just bring it up this way. This is the transform features by scaling each feature to a given range. You can actually change the range to to beyond 0 and 1, or some other numbers that you feel that is useful for your machine learning algorithm. So let's look at MaxApps scaler. Now it works in a very similar fashion, but it scales in a way that the training data lies within the range of -1 and 1. How it does that is that it divides through the largest maximum value in each features It is meant for data that's already centered at 0 or sparse data. So let's take an example. We using the X-train to first of all instantiate, and then we transform the training data, and we'll just print out as this and see what it looks like. So notice that it basically transformed 2 to 1, and the lowest number -1 here to -0.5. Basically, it actually made it in that range there. So notice that one key thing is that it actually perform all of these in a row-wise manner. And when we actually input this, let's just see, comma, invalid syntax. Oh yeah, there's a dot here, extra dot here. And as you can see, it transformed everything and forced it into the range of -1 and 1. Now the key thing to understand this here is that we have multiple features. So this is one feature, this is one feature, and this is another feature. So there are 3 features here. It will actually transform in according to that feature itself. Okay, so that's really very important to understand. It doesn't actually take the aggregate whole. It just takes, you know, each row and the whole column and perform the actual transformation accordingly. Other methods that you can actually perform is scaling sparse data. Now, centering sparse data would destroy the sparseness structure of the data, so it's really a sensible thing to do. Sometimes it does make sense to scale the sparse inputs, especially if the actual features are on different scales. You can either use max absolute scalar or max ABS scalar, where it is specifically designed for scaling sparse data. And it's not really, the point here is that you're not trying to actually center it with the mean of 0. What you're trying to do is actually conform it to a range. Other method that you can conduct is it's whitening rather than scaling. We will cover this topic when we actually get to the PCA, or principal component analysis. The whole idea of whitening really is that it is sometimes not enough to center and also scale the features independently. Sometimes the downstream model can further make some assumptions on the linear independence of the features. You have linear regression. It makes the assumptions that the features are independent of each other. But if that's not the case, you're going to have some errors and some problems with your model. So using PCA, it will actually remove the linear correlation amongst the features, and hence removing the multi-collinearity problem itself. So let's look at the next one, which is normalization. Normalization is the process of scaling the individual samples to have unit norm. Okay, what does that mean? Now this process can be useful if you plan to use a quadratic form such as a dot product or any other kernel to quantify the similarity of any pair of samples. So what you're doing here is you take the individual value minus the mean divided by the range itself. This assumption is that the base of the vector space model often used in text classification and clustering context. Now there are 2 types of normalization. You have the L1, which is also called least absolute deviation, to ensure the sum of absolute value is 1 in each row. L2 normalization is least squares, ensure that the sum of squares is equal to 1. I think it's best to actually use example to illustrate this. Again, while normal data, after it's normalized using L2, which is least squares here, you can see that the data has indeed been transformed. The sums of all the squares is equal to 1. The alternative is that the preprocessing module further provides a utility class called normalizer that implements the same operation using the transformer API. And we have, using the normalizer, you use the norm is equal to L2, and you perform the transformation. And what you can see here is exactly the same as that. And you transform the new data, which is the test data. Quite often, it will just transform any data in accordance to how it was fitted earlier. So coming back to this, the whole basic idea here, really, normalization, is that it scales the individual samples to have a unit norm. What it does is that it conforms to 2 things. Either if you're using L1, the sums of the absolute value is equal to 1. If it's L2 normalization, the sums of squares is equals to 1. Okay, so that's really quite important. Okay, right, binarization is the next and the last transformation, data preprocessing that we can do with our so-called nominal data or numerical data. The feature binarization is the process of thresholding numerical features to get Boolean value. So what I've done here is that you have your observation, you transform it either equal to 0 or 1. Now this can be really useful for downstream probabilistic estimators that make assumptions that the input data is distributed according to a multivariate Bernoulli distribution. Bernoulli basically means it's either 0 or 1, success or fail. It is also common amongst text processing community to use binary feature values, even if the normalized count or TF-IDF values features often perform slightly better in practice. So in any case, the whole idea of binarization is transform your raw data into either a 0 or 1. So let's look at this. This is our raw data. We are instantiating our binarizer. And when we transform the data, as you can see here, it's either 0 or 1. Now the threshold does not have to be 0. You can actually modify it. Notice that here we set the threshold to 1.1. And the number is, well, it really is the same. So if I change the number, let's just say to threshold is equal to 2.2. Let's see what it looks like. Everything becomes 0 then. Okay, so anything that's below 2.2 is basically 0. As you can see here, it gets transformed. Okay, so if I change everything to minus 0.5, then only the minus 1 will be 0. Everything else will be 1. So that's really how a binarizer works. Right, now moving away from working with numerical value, we are working with categorical or non-numeric, such as Australia, Singapore, New Zealand, Hong Kong, country names. It could be male, female. It could be other categorical features. Now, unfortunately, a lot of machine learning algorithms don't know how to directly work with categorical features like this. So what we do is that there are two ways the two main ways that people transform. I'll just talk about the first one, which is called label encoder. Again, from the pre-processing library, we instantiate the label encoder. I'll call that label_ec. And we transform the source data, which is this one, to SRC. Okay, having transformed that, we let's just print the country to code mapping so that you can actually see what it looks like. So this is the value, this is the K, which is the number. So you have Australia 0, Hong Kong's 1, New Zealand's 2, and Singapore is 3. That's really the actual mapping itself. In essence, what you have is actually an alphabetical ordering here. Now, that's really how the transformation is done for label encoder. In essence, it actually codes it into numerical value. But there's a problem with this. A lot of machine learning algorithms going to look at this and say, hey, Australia is 0 and New Zealand is 2, so New Zealand is actually more important than Australia. And that can create a problem when you're trying to build a machine learning model. Obviously, these 0, 1, 2, 3 has no meaning apart from the fact that it's just being transformed. So it doesn't actually contain any so-called value or any inputs in such a way that actually have any predictive value for your target. So quite often what people do is actually they take this raw number and perform what's called a one-hot encoding. And one-hot encoding is really useful for dealing with sparse matrix. It uses also what's called one-of-k scheme, the process of turning a series of categorical response into a set of binary results 0 or 1, which render it completely meaningless to the algorithm itself, except that it's useful now because the 0, 1, 2, 3 here doesn't have meaning, but the country itself does have meaning. So let's pull the two things that we did here. The source is the original source. The SRC is what we did in terms of transformation using the label encoder. And we're importing now the one hot encoder. We're instantiating here encode one hot underscore and enc, and we transform the data so that we can actually perform the fit transform. And now look at what the one hot looks like after it's been transformed. Take the SRC, which is this one here, and transform it, and this is what it looks like. So what you have is 1000 being the first one, Australia, Singapore is 0001, New Zealand is 0010, and Hong Kong is 0100. And in essence, what has been done really is that it's transformed into a sparse matrix and is extremely useful now. It's actually basically have four features, and this can be used as your input into your or the predictor of your machine learning algorithm. So how do you invert that? You can use this, basically the first one, the 0 column, or the first row, sorry, I should say, is Australia. The third, which is our fourth, is actually Hong Kong. So that's really how you actually use this transformation method to convert categorical data into numeric, so that your machine learning algorithm can actually use that as a feature or as input value. I've provided some references for you to, if you are interested to study more. So that's really the end of the lesson itself. In the previous lesson, we started with data preprocessing. We talked about scaling the data itself into pretty much what a statistician likes, with a mean of 0 and standard deviation of, of 1, or variance of 1. Okay, and that's really standardization or mean removal or variance scaling. And the next algorithm we cover is min-max, basically between 0 or 1, or you can scale it to a range that you like. And the next one is the max absolute scalar, which is part of the min-max. And we talked about normalization. Basically, there are two types. L1, which makes sure that all the absolute value of all the numbers sums up to 1. L2 normalization makes sure all the sums of squares is 1. Again, those are operating on row. Binarization is really transforming your raw data into either 0 or 1. And then finally, we talk about categorical features and how to actually transform them into something that your machine learning can use as features. We demonstrated label encoder to encode these into basically numerical number, and we further transform it using one hot encoding, because 0, 1, 2, 3 does contain or imply that one is more important than the other. So after we use the one hot encoder and transform it, what we get instead is the sparse matrix here, whereby it is just binary in nature. Now you can actually put it into your machine learning algorithm as an extra feature without distorting your machine algorithm by implying that there is a ranking here, which is obviously not the case. So I'm going to ask you to pause the video, and I'd like you to actually get your hands dirty and try using a slightly different categorical value and try that out. I've summarized this video now. Let's just pause this video, and when you come back, I'll tell you what we're going to go through in the next lesson. I hope you gave it a try, and with all the different algorithms, the min-max, the one-hot, the binarization, and actually get some intuition and really understand how this can be used for your machine learning algorithm. And when we come back, the next video, we're going to go into variance bias trade-off. I'll see you then.